Good morning, dears. Welcome back to our physics class. And in the last class, we have discussed about the magnetic effects of electric current, right? That is, what is magnetism, electromagnetism, and what are magnetic field and field lines, and how we can predict the magnetic field strength, and how the magnetic field is produced due to a current carrying conductor and a straight conductor, circular loop, solenoid, and how we can make a electromagnet. That are all things we have discussed, right? So now we are moving to the next topic, that is force on a current carrying conductor in a magnetic field. Okay, so there should be a force associated with this magnetic field on a current carrying conductor. Okay, so we can look into your textbook. We have learned that an electric current flowing through a conductor produces a magnetic field. Right? Definitely, we know if current carrying conductor will produce a magnetic field, right? And the field so produced exerts a force on a magnet placed in the vicinity of the conductor. Okay, so if we place a magnet in the vicinity of this conductor, there should be a force exerted. A force exerts on this magnet, right? And French scientist Andre Marie Ampere suggests that the magnet must also exerts an equal and opposite force on the current carrying conductor. Okay, so when current is passing through a conductor, that produces a magnetic field, and that magnetic field exerts a force when we place a magnet near the conductor, and also that magnet also produces an equal and opposite force to that conductor also. Okay, so the magnet must also exert an equal and opposite force on the current carrying conductor. The force due to magnetic field acting on the current carrying conductor we can identify using this activity 13.7. Okay, so there is an activity given to you to identify how this force acting on this conductor, and how what is the direction, and that all things we can discuss by doing this activity 30.7. So what is the activity? Take a small aluminum rod and using two connecting wires, suspend it horizontally from a stand. So the figure is given here. That is, we have a stand. So I'm not good in drawing. Suppose this is a stand, and then we place that is a aluminium rod AB. AB is the aluminium rod. You can look into the figure 13.12. Okay, aluminium rod is suspended. Aluminium rod is suspended using two connecting wires. Okay, so here a circuit is constructed here. Okay, so the one end of that wire is connected to the end of the aluminium rod, and another end here we have a cell and a battery and a key. Here we have a key, here we have a cell. This is positive terminal, this is negative terminal, and this is a variable resistance, this is a resistance. Okay, so here a magnet, a horseshoe magnet is placed. Right? So, it has a south pole and north pole. Right? So, place a strong horseshoe magnet in such a way that the rod lies between the two poles with the magnetic field direct upwards. So, the magnetic field should direct upwards. So, how we can place that? For that, the north pole of the magnet vertically below the south pole vertically above the aluminum rod. Okay, so we have to place like this. So this is the south pole of the magnet and this is the north pole of the magnet. Okay, so the north pole of the magnet vertically below the south pole. Vertically below the south pole. So this is south pole, this is north pole. Vertically below the south pole, north pole is placed. And then below and south pole vertically above the aluminum rod. South pole vertically above the aluminum rod means this is aluminum. Suppose this is aluminum rod. So here the south pole and here we have north pole. Okay. So that is how it is connected. And connect the aluminum rod in series with the battery, key and rheostat. So here we have a variable resistance, that is rheostat, and here we have a cell and key. Okay. So now pass a current through the aluminum rod from end B to A. So here we have the end B and A, aluminum rod AB. Okay. So current passing from B to A, and we can observe that the rod is displaced towards the left. So the rod should be displaced towards the left. If current is passing through this circuit, that is from B to A, then we can see that the rod is displaced towards the left. Okay. And if we reverse the current, that means if we replace this positive terminal, if we reverse this positive terminal and negative terminal, interchange these terminals, then the current should be reversed, right? So what happens then? Then we can see the rod will move towards the right. Okay, that means if we reverse the direction of current, then also the displacement of the rod also reversed. That means first it changes, it displays to left, and if we reverse the current, then it is displays to right. Okay. So the displacement of the rod in the above activity, in this activity, suggests that a force is exerted on the current carrying aluminum rod. So a force is exerted on this aluminum rod. Okay. So this aluminum rod carries a current, right? Due to that current, there should be a magnetic field. There produce a magnetic field, right? So if we place this magnet in that magnetic field, these magnets exert this the magnetic field exerts some force on this magnet, and this magnet also exert equal and opposite force on this current carrying conductor, right? That force displaces this rod towards right or towards left, right? Okay. So when we change the direction of current, the displacement also changes. That means the force become reversed, right? Okay, so that force depends upon this current. And the direction of force is also reversed when the direction of current is current through the conductor is reversed. Now change the direction of field to vertically downwards by interchanging the poles. So now we have here south pole and north pole, so the magnetic field is upwards, right? Okay, so the magnetic field should be upwards, and if we interchange these poles, that means if north pole is placed here and south pole is placed here, then the magnetic field direction also reversed. That means the magnetic field towards downwards. Now the magnetic field become downwards, directed downwards. And then also we can see that there is a change in the displacement. The direction of displacement also changes with the change in the direction of magnetic field. Okay. So the direction of force acting on the current carrying rod is get reversed when the magnetic field get reversed. Okay. And it shows that the direction of force on the conductor depends upon the direction of current and the direction of magnetic field. Okay. So the direction of force, that direction of force is just this displacement is due to the force, right? So that force, the direction of force depends on the direction of current and magnetic field. Direction of magnetic field. Okay. So the displacement of the rod is largest. So we can find, or the experiments has shown that the displacement of the rod is largest. The displacement is largest means the magnitude of force. The force experienced by this rod. That is due to that force, the rod displaces left or right. Okay. So the displacement of rod is largest when the direction of current is at right angles to the direction of magnetic field. In such conditions, we can use a symbol rule to find the direction of force in the conductor. Okay, so here comes the Fleming's left hand thumb rule. Okay, so the force, the direction of force, we have to find the direction of force, right? So if we know the direction of current and the direction of magnetic field, then easily we can find the direction of force using Fleming's left hand rule. Okay, so experiment shows that the magnitude is more, or the displacement of the rod is largest when the current and the magnetic field are right angles to each other, right? Okay, so if it is the magnetic field and it is the current, then we can say that the displacement or the force experienced by this rod is maximum, right? That means they are right angle to each other. Okay, that means the force is largest when the current and the magnetic field are right angles to each other. Okay, so now how we can find the direction of magnetic, how we can find the direction of that force, that we can use the Fleming's left hand rule. How we can find, that is what does it says? The direction of current and the direction of magnetic field perpendicular to each other, and found that the force is perpendicular to both of them. Okay, so if the field and current are perpendicular to each other, then the force is also perpendicular to both of them, right? So here we can see the force, direction of force. Okay, so the three direction can be illustrated through a symbol rule called Fleming's left hand rule. According to this rule, stretch the thumb such that they are stretch the thumb, forefinger and middle finger such that they are mutually perpendicular to each other. The first finger points in the direction of magnetic field and the second finger directs the current. Then the thumb will point the direction of motion or the force acting on the conductor. Okay, so this is what Fleming's left hand rule says. That is, if this is the field, the direction of magnetic field, this finger represent the direction of magnetic field and this will represent the current. Okay, so these are mutually perpendicular, and also this thumb is mutually perpendicular to both these fields. That means this field and the current. The thumb is mutually perpendicular to both of them. That means this will represent the force acting on the conductor. Okay. So that is Fleming's left hand rule. So what it says? Fleming's left hand rule says that if we stretch the thumb, forefinger, middle finger of our left hand mutually perpendicular, then the first finger points the direction of magnetic field. First finger means this finger. Pointing finger shows the direction of magnetic field, and then the middle finger points the direction of current. Then the thumb will point the direction of motion or the direction of force acting on the conductor. Okay, so devices. This is the simple rule to find the force acting acting on a conductor, that is produced by the effect of magnetism, right? Okay. A current carrying conductor will produce a magnetic field, and that magnetic field also exerts some force on this conductor. Okay, so to find out the direction of that force, we can use Fleming's left hand rule. Okay. So devices that use current carrying conductor and magnetic fields, including electric motor, electric generator, loudspeakers, microphones, and measuring instruments like radios, hearing aids, that all equipments use this current carrying conductor and magnetic fields. Okay, so we have to study some of them in detail the coming classes. Okay, so now you can see the example 13.2. What it says: an electron enters a magnetic field at right angles to it, as shown in figure. That is electron. Now we know how to find that direction of force using Fleming's left hand rule, right? Okay, so here in example 13.2, it is given that an electron enters a magnetic field at right angle to it. So this is the direction of electron. Okay, and right angles to magnetic field means this will be the direction of magnetic field. This will be the direction of magnetic field. Right angles to it means it is like that. It is entering to this magnetic field. If it can also enter from this way to here, right? Like this. Okay. So in your textbooks, it is given that the electron is entering like this. Okay, that is perpendicular to the magnetic field. And the direction of force acting on the electron will be. So what will be the direction of force acting on the electron? That is, options are given: to the right, to the left, and out of the page, into the page. So how we can find? We can use Fleming's left hand rule to find out the answer. So the answer is actually option D, into the page. That means the direction of force is perpendicular to the direction of magnetic field. Okay, so the direction of force should be perpendicular to the direction of magnetic field. Using Fleming's left hand rule, we can say the force is mutually perpendicular to the field and current, right? Here instead of current, it is given that the coming electron, right? Okay, so current, it is the flow of electrons, right? Okay, so here it is given electron entering right angles to the magnetic field. And also we know from the Fleming's left hand rule, but magnetic field should be the force experienced should be right angles to each of them. That means magnetic field and current. Okay, so the force should be perpendicular to the direction of magnetic field and current as given by left hand rule. and the direction of current is taken positive to the direction of motion of electron. Okay, so the direction of current in the direction of electron is taken as positive. Okay, that is this we have already studied in the electricity chapter, right? The direction of current is taken, the direction of current is taken opposite to the direction of electron. Opposite to the direction of electron means if electrons are moving in this direction, what happens? The direction of current is taken opposite to this, right? That is കറണ്ട് കണ്ടുപിടിക്കുന്ന ടൈമിൽ ഈ ഇലക്ട്രോൺസ് ഒന്നും കണ്ടുപിടിക്കാത്തത് കൊണ്ട് അന്നുള്ളവർ എന്താണ് ഇലക്ട്രോൺസിന്റെ മൂവ്മെന്റ് കൊണ്ടാണ് ഈ കറണ്ട് ഉണ്ടാകുന്നതെന്നൊന്നും മനസ്സിലാക്കാതെ ആണ് അവർ കറണ്ട് ഉണ്ടെന്ന് മനസ്സിലാക്കി. ബട്ട് ഇലക്ട്രോൺസിന്റെ മൂവ്മെന്റിന് ഓപ്പോസിറ്റ് ആണ് കറണ്ട് ഫ്ലോ ചെയ്യുന്നതെന്ന് പിന്നീടാണ് ഡിറൈവ് ചെയ്ത് വന്നത്. ഓക്കെ, സോ in the chapter electricity we have found that the direction of current is just opposite to the direction of motion of electrons. Okay, so as we know, direction of current is taken opposite to the direction of motion of electron, then the force is therefore directed into the page. So it is like this. If electron motion movement is like this, so the current, what we can see, the current is in this direction, right? Opposite to this direction. So these are mutually perpendicular. So what will be the direction of this force? It should be perpendicular to both of them, means into the page, right? So we cannot represent it on this board. That means it's a three-dimensional figure. Okay, that means if we represent, this is the what magnetic field, and this is the what current, the direction of current, right? And this will be the direction of force. Okay, so here we have magnetic field, and in this direction we have current, and definitely the force should be in this direction, but we cannot write this on a page or in a blackboard. Okay, so the force should be into the page. Okay, so that is the example 13.2. and some of the questions given to you. Question: which of the following property of a proton can change while it moves freely in a magnetic field? So there may be more than one correct answer. That is options: A is mass, B is speed, C velocity, D momentum. So what are the things changed? Which of the following property of the proton will change? Yeah, velocity will change, also momentum will change. That means momentum, we know what is the equation of momentum. It is mass into velocity. If velocity changes, then also momentum also changes, right? Okay, so some other examples is also given, some other questions is also given to you, 2 and 3, that you should do as homework. Okay, so you should do that as homework. So here it is given more to know magnetism in medicine. What it says: an electric current always produces a magnetic field. Even weak in iron currents that travel along a nerve cell in our body produce magnetic fields. Okay, so you have to do all that questions as homework, that 3 questions. Okay, so here it is given more to know, it is magnetism in medicine. So this magnetism has developed or magnetism has importance in medicinal world also, right? That is, an electric current always produces a magnetic field. That we know, an electric current always produces magnetic field. And even weak ion currents that travel along the nerve cells in our body produce magnetic field. So, നമ്മുടെ ബോഡിക്കകത്ത് ഇൻസൈഡ് അവർ ബോഡി ഒരുപാട് ബയോളജിക്കൽ ആക്ടിവിറ്റീസ് നടക്കുന്നുണ്ട്, ബയോളജിക്കൽ പ്രോസസ്സുകൾ നടക്കുന്നുണ്ട്, റൈറ്റ്? സോ നെർവ് സെൽസിൽ ഇൻ അവർ ബോഡി weak ion currents that travel along the nerve cells in our body produce magnetic fields. That ion currents means the flow of charge make in electricity, right? So weak impulse or weak electricity current may produce when these ion currents that travel along the nerves in our body produce magnetic field. Okay, so when we touch something, our nerves carry an electric impulse to the muscles we need to use, and these impulses produce a temporary magnetic field, and these fields are very weak and are about 1 billionth of Earth's magnetic fields. So Earth magnetic field is too much high when compared to our the magnetic field produced inside our body, right? So inside our body there is a small weak ion currents are there, and that produces very weak magnetic field. Okay, when comparing to the Earth's magnetic field, it is too much small, right? That is 1 billionth of Earth's magnetic field. Okay, so two main organs in the human body where the magnetic field produced is significant are the heart and the brain. So heart and the brain that produces some amount of magnetic field or a significant magnetic field. Okay, so that are the heart and brain. The magnetic field inside the body forms the basis of obtaining the images of different body parts. So നമ്മൾ MRI എടുക്കുക എന്നൊക്കെ പറഞ്ഞിട്ടില്ലേ? MRI means magnetic resonance imaging. So inside our body there should be a significant magnetic field is produced by our brain and heart, right? Okay, so that we can use to image our other body parts. MRI images ലഭിക്കാൻ നമ്മളെ ഈ ഓർഗൻസ് ആയിട്ടുള്ള ബ്രെയിൻ ആൻഡ് ഹാർട്ട് പ്രൊഡ്യൂസ് ചെയ്യുന്ന മാഗ്നറ്റിക് ഫീൽഡ് കൊണ്ട് നമുക്ക് മറ്റുള്ള ബോഡി പാർട്സിൻ്റെയൊക്കെ MRI ഇമേജസ് എടുക്കാൻ സഹായിക്കുന്നുണ്ട്. ഓക്കെ, so the magnetic field inside the body forms the basis of obtaining the image of different body parts. This is done using a technique called magnetic resonance imaging. Analysis of these images helps in medicinal diagnosis, and magnetism has got importance uses in medicine. So MRI ഉപയോഗിച്ച് നമുക്ക് ഇന്റേണൽ ബോഡി സ്ട്രക്ചറിലെ ഡിഫക്ട്സുകൾ അല്ലെങ്കിൽ ഡയഗ്നോസ് ചെയ്യാനൊക്കെ നമ്മൾ MRI സ്കാനിങ് യൂസ് ചെയ്യാറുണ്ട്. ഓക്കെ, so that is how magnetism is important in medicinal field. Okay, so inside our body there also produces some magnetic field, some the ion currents that produce some magnetic field. That is not that much of significant, but brain and heart produce significant amount of magnetic field that helps to diagnose, or that helps for magnetic resonance imaging, MRI. Okay, MRI എടുക്കാൻ ഉപയോഗിക്കുന്നുണ്ട്. Okay, so it helps to diagnose the diseases and all the internal damages like that things. Okay, so this is how magnetism has got importance in medicinal world. Okay, so these are the some importance of magnetism, and in the coming classes we have to study electric motors and how it works and what are the features of these electric motors and that are things. Okay, so that we will discuss in the coming classes, and you should write your homeworks neatly in your notebook, and you have to submit in the coming days your notes in the coming days. Okay, so children, we can meet in the coming classes. Till then, take care and goodbye. Thank you.